Hi, and welcome to this different style of GCSE chemistry paper walkthrough. This is a paper 1 style, as we've said on previous videos, based on AQA syllabus, but this one is going to be slightly different in structure in that it's comprised of more structured questions, so plenty of multiple choice, filling in the blanks and then dot to dot type questions. It's going to be focusing on more factual recall, descriptions and some slightly simpler calculations. So if you are wanting to sit the foundation tier, this will be really good revision, covering the same topics on paper 1. But also if you're sitting the higher tier, this will be good for just some quick fire revision as well. So according to the numbers of marks available, this is an hour and 45. But hopefully we can try and rattle through this a little bit and try and make it a little bit more factual, quick recall type revision. So let's get straight into it with question number 1. Standard start to a paper with atomic structure, asking us just very simply to select the relative words to complete these sentences. So if we have an atom, the central part of that atom is, as we know, called the nucleus. So that's one word gone. And the particle with no electrical charge, which is also in the nucleus, is the neutron. So remember, the neutron goes in the nucleus, so both beginning with N. That sometimes helps remember that. And the particles with a negative charge moving in shells go around the outside. So try to answer the question there in that it's not asking you for the name of those particles, which are the electrons, remember, but they are moving in shells around the center. Okay, remembering also the protons would go with the neutrons in the nucleus while we're here doing a bit of revision, and obviously the electrons going around that nucleus in their shells. So nice start to this one, 3 marks there. We've got then this next question with an atom of magnesium having an atomic number of 12. So if we were on the periodic table, this would be a 12 down the bottom corner with a mass number of 24 up on the top. So we have to complete this table asking us for the number. So first job is we take the bottom number. The bottom number tells us the number of protons. It is the atomic number, it's also known as a proton number, and by definition tells us the number of protons in an atom's nucleus. Because an atom is also neutral, and we know that protons are positive, the P for positive, P for proton, and that electrons are negative, we know that there are also 12 electrons. They have to balance each other out. And the way in which we calculate the number of neutrons is to take the top number and simply subtract the bottom number. Now it does give us 12 again. That's not always the case in atoms, but in this situation we have 12 of each particle. So if we go further down then, this is then going to ask us to hit an electronic structure of a chlorine atom with, it's given us the actual electron configuration here. If we were again looking at the periodic table, the bottom number would have been 17, giving us rise to 17 protons and then subsequently 17 electrons. And this is asking us to draw a diagram to represent that 287. So when you are drawing an electronic arrangement diagram, you have to always start with the nucleus. You don't necessarily have to label it as a nucleus or draw the numbers of protons and neutrons within it, but always ensure there is a dot at the center of your diagram to illustrate that the nucleus is there. And then we enter in the shells around the outside. So we've got 287, so we know we've got 3 different numbers there, and therefore 3 shells. And we place 2 electrons on that first shell. The 8 electrons go on the second shell, meaning we've used up 10 of those electrons, and the remaining 7 go onto the outer shell of that chlorine, and we finish that atom off as there. So we've got, as it says in the question, 2 in the first shell, 8 in the second, and 7 in that third one. So the next question asks us about neon, which is in group 0, the periodic table. You may also see that written as group 8 as well, depending on the periodic table you're reading at the time. And it's asking us why neon is unreactive. Now, because it's in group 0 or group 8, it's possible to appreciate that if it's got 8 electrons in its outer shell, then it does not need to gain nor lose any electrons in order to complete that one. If it was to pull in one more electron, that would have to go into a subsequent shell around the outside. So that would have to go into there if it was going to gain an electron. And if it was going to lose an electron, it would have lost one of the electrons in its outer shell, and that would have then lost its complete shell situation. And so it doesn't want to do that, and that is ultimately the reason why neon is unreactive. So in order to answer the question, neon has a full outer shell, which is point number 1, and because it's got a full outer shell, it doesn't need to lose nor gain, doesn't need to lose or gain an electron. And always make sure you're talking about electrons, obviously. And just to make sure we're also covering both bases in terms of losing or gaining electrons is more ionic style bonding. But we'll make sure that we also cover the covalent aspect and saying that it doesn't need to lose nor gain an electron or indeed share electrons. And so that will allow us to pick up both marks on that question. And that moves us straight into the next question, which is now, again, quite often you find an atomic structure question then moves into bonding of more compounds and molecule type situations. And so here we're being asked to join the dots between the substance type on the left and the description of what is being described there. So in the first one, we're being asked to look for the ionic compound, and ionic compounds are compounds made of positive and negative ions, which are oppositely charged, and so we can see that definition nicely in that second point there. And simple molecular substances, molecules, are formed when covalent bonding occurs, and that is done when we share electrons, which means that metallic substances, which is the one which is left, but we know that this is the definition of metallic bonding really, where we've got this regular arrangement of positive ions with a sea of delocalized electrons. And so we're happy that that third one is good for that one. So moving on into 2.2, this question's asking us for a bit more explanation this time, so we'll need to have a little bit more detail about what's going on. But here we have sodium chloride, and it's telling us that the melting point is 801 degrees, and it's asking to us explain why sodium chloride has a very high melting point. So when we have these types of questions, it's quite often a good idea to identify the bonding type first of all. And in sodium chloride, we have a giant ionic lattice, giant ionic structure. And so once we've established what the type of bonding is, it's then often a good idea to explain how that bonding is held together. And so this is held together by strong electrostatic forces of attraction. And that's a good definition and a good phrase to try and learn really. So held together by strong electrostatic forces. That aspect of strong also starts to illustrate and answer the question as to why it's got a high melting point. So we're starting to get the scale into what we've got here. And to give this a bit more definition of Now, what an electrostatic force is, so we can extend this a little bit further by saying it's held together by strong electrostatic forces between oppositely charged ions. So it puts a little bit more detail into that. Charged ions, and again, that ions brings it back to ionic lattice, that being between, in this example, Na plus and a chloride minus ion. And because we're talking about melting, or if we were talking about boiling, we'd have to be talking about temperatures which have been generated and therefore energy. And so to relate all that together, so giant ionic lattice held together by strong electrostatic forces between oppositely charged ions, which is the explanation. And then to just kind of finish it off, therefore a large amount of energy needed. And that then kind of brings the question together and ultimately then finishes that off. And we bring it around in a circle by again mentioning the forces that we mentioned at the beginning of the question and illustrating that the energy is then used to overcome those forces, hence why it will subsequently melt. And so it's a nice question based around that, and we've attacked it in a nice linear fashion so that we don't get too repetitive throughout our answer. So ionic in question 2.2 with sodium chloride, but now we're going into a water question whereby we have a molecule, and this one is asking us why water does not conduct electricity. So electricity is conducted via either the movement of ions or by delocalized electrons. So you need either an ionic substance to be either molten or in solution, or you need a metal with delocalized electrons, or the exception being graphite, obviously. So water is none of those. It's a simple molecular substance, and therefore the simple molecular substance has no charged particles. So electrons are negatively charged, ions are obviously either positive or negatively charged, and so because water is a molecule, it has no charged particles. And the reason why it therefore cannot conduct electricity, to then link those two things together, is that there's no charged particles, so it has no charged particles that can carry charge. And we always like to put that phrase into an answer because that's illustrating we know what electricity is and how electricity is conducted through a substance. So through the substance. And then that answer, that final part of that answer can then be applied to anything in terms of conduction. If we were talking about metals, we'd be talking about no electron or electrons that are carrying the charge. If it was ionic, it'd be ions which are carrying the charge. But in a molecule, because we don't have those charged particles, there's nothing there that can carry the charge, and therefore it does not conduct. So moving on again quickly into 2.4, we have a question now about diamond and graphite, so two allotropes of carbon, and it's asking us for one similarity and one difference. Now both diamond and graphite are giant covalent structures, so in the same way that salt, sodium chloride, was a giant ionic structure, this is a giant covalent structure made up of many bonds, many atoms, very strong bonds, etc., etc. If this was to have been a slightly longer type of question, but a simple similarity is it's a giant covalent structure. You could alternate the word structure for lattice, that's often an acceptable route out as well. An alternative would have been that both diamond and graphite are, as we said, and it also says in the question, are both made of only carbon atoms. So we're not strictly repeating the question. So it does say 2 forms of carbon, but we're actually just getting a little bit more specificity of saying they're both made of carbon atoms only. So it's just allowing us to illustrate that we know that it's just 2 different forms of the same element. However, differences being, diamond is a very hard substance and graphite is relatively just not. So diamond is hard. It's hard because it has 4 bonds per carbon, whereas graphite only has 3. And so with these, obviously you would need to probably give the alternative as well. So you would probably say diamond is hard, but graphite is soft. So we would give kind of both to illustrate the difference. So diamond is hard, but graphite is soft, and to allow us to link the other point, in diamond we have 4 bonds per carbon, in graphite we have 3 bonds per carbon. And so we've got 2 possible differences there, both of them showing that both the different properties are different structural differences between diamond and graphite, and linking those 2 together. So again, moving on, as I say, we're trying to make this paper a little bit quicker. We're not doing as much explanation, trying to make it a little bit more rapid fire here. So we're straight into question 3, a calculation. It's asking us to calculate the relative formula mass of magnesium oxide. Now it's given us the formula, which is MgO, which means we've got 1 magnesium and we've got 1 oxygen in that atom, in that compound, sorry. We have the relative atomic masses of both of those substances being 24 and 16. We only have 1 of each of them, so we don't need to do any multiplication, but we add those together and we get a nice 40 there as the relative formula mass of magnesium. So as we said in previous run-throughs, I generally use the term RFM, meaning relative formula mass, but you may also see, depending on your book and course, you may see MR, you may see RMM, and various permutations thereof. But this is relating to the mass of the compound versus the relative atomic mass being the mass of the singular atom. But as I say, I'll try to use RFM consistently, but just be aware you may see different terminology depending on what you're reading at the time. And so now we've got that RFM of 40 for the magnesium oxide that we've just calculated there. We're also told in the next question that we have 48 grams of magnesium, and the question is asking us to convert that 48 grams into a number of moles. And so the equation we need here is moles equals the mass we have of the substance we're looking at divided by its RFM. And for this one, we're asked to look at the magnesium, so we know we've got 48 grams of it, which we're given in the question, and we're given the RAM of magnesium in the previous question again. If you just look at the top of the page there, which was 24, 48 divided by 24 is 2, so we know that we are using 2 moles of magnesium. Using 2 moles of magnesium in this question is quite useful because we've got a 2 there in that balanced equation. And in this next question, it's asking us to appreciate and calculate the mass of magnesium oxide that is being produced. So the student wants to produce 2 moles of magnesium oxide, which is the number given in that equation. So that kind of makes sense for this procedure. And it's asking us to calculate the mass of magnesium oxide. So what we have to do is take the previous equation that we used and rearrange it so that mass becomes the subject of this equation. This will then give us moles multiplied by the RFM this time in a rearrangement. And the question is asking us to calculate it for 2 moles. multiplying by the RFM. The RFM, if you remember, we calculated in the first question. It's telling us to use our answer for 3.1. So if we hadn't got the number 40 here, you would get full carry forward marks in your answer. But using the number 40 in our situation, doubling that up, times it by 2, gives us the mass of magnesium oxide as 80 grams. So as I say, even if you hadn't got 40 in that previous question and you'd perhaps got a different number, as long as you'd multiplied it by 2 in this question, you would still get access to both of these marks. So it's quite often a good idea to carry on, even if you're not certain at a certain point, but to carry on if you know that that question was a doubling of it. You would still pick up some marks along the way. So if we're then asked in a question about what a yield is, the yield is ultimately how much of a product we get from a reaction. So it is that the yield is the, now don't usually like using the word amount, but in this one it arguably makes a bit more sense. So it's the amount, it's the mass, it's the number of moles, etc. But it's the amount of product made from a reaction. And quite often you would then be asked to calculate a percentage yield in a question, and that's exactly what happens in this next question. So a reaction, we're told here, has a theoretical yield of 50 grams, but we only make 40 grams. So it's asking us to calculate what the percentage yield of that equation, of that experiment is. They've given us the equation that we need to use, and we take the actual yield, which is 40. We divide it by the theoretical yield, which in this example was 50. And in order to manufacture a percentage, we multiply by 100 to get the maths right, and plugging those numbers into a calculator, we get an 80% yield using those numbers. Of course, sometimes you may be asked to generate yields in previous questions using the mass, moles, RFMs from the equations. In this example, we were given them directly in the question, but it's quite nice here that they've given us the equation as well. So moving then into another question on here, a student this time has reacted 1 mole of carbon, so we know we've got 1 mole here, with 1 mole of oxygen to make carbon dioxide. Now the balanced equation has 1 carbon on the left hand side, 1 molecule of oxygen on the left hand side, and that will make 1 molecule of carbon dioxide, which means we don't have to do too much fanciness with the RFMs and ratios, but in the first instance we do need to calculate the RFM of carbon dioxide, and so we need to know those numbers. Now they haven't given us them in this specific question, but if we were to use the periodic table, we would be able to generate the mass numbers of both of those atoms, being carbon 12 and oxygen 16, those being the top numbers of their atomic symbols. So if carbon dioxide has 1 carbon and indicated by this O2, it has 2 oxygens, we know that we will need 2 lots of 16. If we add all that together, we will get 44. That gives us the RFM of carbon dioxide. We know from a previous question that in order to calculate the mass of a substance, we need to know the number of moles of it, and we need to know the RFM of it. The RFM, obviously, we've just calculated as 44. The number of moles we know is 1 from the equation, and so we end up with 1 times 44 as our final calculation, giving us obviously a mass of 44, because we're only multiplying it by 1 this time. But again using this equation and its rearranged forms. So a very good equation to try and learn, trying to learn or memorise all of its rearranged forms, or be happy to be able to rearrange it in an exam if you needed to. So moving on again, we're into question 4. This one's about reactivity series and extraction of metals, and this question is asking us to put the metals into their order of reactivity. Now, they've not given us any experimental data here, so this is a bit of factual recall. Now, we can look at their positions on the periodic table, and we know that potassium is in group 1, and each of copper, iron, and zinc are all transition metals. Now, we know that group 1 metals are the ones which are generally very reactive substances. They react quite violently with water sometimes, and so we can be quite confident of placing potassium there. The remaining 3, we have to try to have a little bit of general knowledge of these. Now, we know from metal extraction reactions that they're all displaceable by carbon, so they're all relatively similar. But we know from a lot of experiments when we do displacements with acids that copper doesn't react with acids, and so whereas iron and zinc can do, and so copper is a very unreactive metal. We kind of know that as well because copper piping in your house doesn't generally react with the water which is there. It doesn't generally rust necessarily, corrode, in the same way that we know that iron definitely rusts. So that observation of iron rusting much faster and to a greater extent than copper shows that iron is probably more reactive than copper, and likewise zinc. Now, we have to have a bit of a think here about whether iron or zinc is more reactive than each other, but one of the uses of zinc, again this comes back to a kind of general knowledge and an appreciation of something such as rusting of the iron, and zinc is used as a galvanizer for iron and can be used in sacrificial protection of iron depending on the way in which it's used. But zinc does that by offering itself up to oxygen so that the iron is not corroded. So essentially zinc either acts as a barrier or as a sacrificial protector, again depending on how it's attached and placed next to the iron, whether it's coated with it or whether or not it's placed as a block on the side. But the zinc, because of that, is able to act as a protector of iron because it's more reactive. And so anything which wants to react with the iron will choose to react with the zinc first. A little bit of kind of general knowledge there really, and a bit of memory too. A lot of experiments you would see, quite often these questions would be given with some experimental data to allow you to evaluate the reactivity, but sometimes it's quite helpful to memorize a little bit of it. There are plenty of mnemonics kicking around to allow you to remember the reactivity series, but those 4 metals can be placed into that order as such. And so iron can be extracted from its ore, iron oxide, by heating it with carbon. That was one of the ways we just discussed. So we have to complete this sentence by saying in this reaction the iron is reduced because it has lost oxygen. So if it gains oxygen, that would be called oxidation. This has been reduced and therefore it has lost the oxygen that it's attached to. So the iron oxide just becomes iron. However, aluminium cannot be extracted from its ore by heating with carbon. And this is because aluminium is more reactive than carbon. And so when aluminium is in its ore attached to oxygen, the carbon is not strong enough to pull it from the aluminium, and so the aluminium keeps hold of the oxygen and the carbon simply just isn't strong enough. So aluminium is more reactive than carbon, and so carbon cannot displace it from its ore. And that allows us to explain that one. So the metal extractions is all about the reactivity series. So the metals on the top are able to kick out metals which are lower than them in the reactivity series. So as we move further down then, this then takes us to gold and taking us to the bottom of the reactivity series, where gold is a very unreactive metal. And how do we know this? Because when we find gold in the Earth's crust, the gold is found pure. It's found as the pure metal. If we find pieces of gold, it is simply just gold atoms that we see. It's not combined with any oxygens, it's not an ore or anything like that. It's just simply found as its natural gold atoms as a pure metal. It's also known as a native metal, or simply as an uncombined element. It's not been bonded to anything. Typically oxygen, occasionally sulfur, obviously in ores, but for gold it's just found as the metal. That process of oxidation and having to subsequently reduce it from its ore is not required. Gold, silver, platinum, for example, they're all found in the Earth's crust as you would want to find them because they're very unreactive. So copper then, when it is heated, reacts with oxygen to form copper oxide, and this is what happens naturally. So metals in the Earth's crust and things will quite happily combine with oxygen to make these ores, these these oxides, in this example copper oxide. So this equation is asking us to balance this equation up. So we have here 1 copper on the left hand side, we have 2 oxygens on the left hand side as well, but on the right hand side we have 1 copper, but we only have 1 oxygen. So on the right hand side we simply don't have enough oxygens. Therefore, in order to do that, in order to make 1 oxygen become 2 oxygens, we need to double up the number of copper oxides on the right hand side. So this doubles up the number of coppers and also the number of oxygens. And because I've done that, the coppers now no longer balance either, which means I now need to make this into a 2 by doubling up the number of coppers on the left. And so we have 2 moles of copper reacting with 1 mole of oxygen molecules to make 2 moles of copper oxide product. So moving further down then into question number 5. This one is more about neutralization and salts this time, so a different type of question, and it's telling us that this reaction is between sulfuric acid and potassium hydroxide. So we've got the acid, we've got the base. In this situation it's an alkali, and acid plus alkali reactions generate salt plus water. We've got the water already, so we're being asked to find and identify the salt. The salt comes from the displacement of the metal in the alkali by hydrogen, generating a potassium type of salt in this example, and a sulfuric acid generates the other half of the salt. And as we've said in many of these papers now, sulfuric generates sulfates, nitric generates nitrates, hydrochloric generates chlorides, etc. And so we're trying to look for these common roots and stems of names, and so we end up with potassium sulfate salt in this example being generated. As we say, if it had been nitric acid, we'd have generated potassium nitrate, and so on and so forth. If we'd have had lithium hydroxide instead of potassium, we'd have generated lithium sulfate, etc., etc. And so we're looking for, as we say, commonalities in the words to allow us to identify those salts. This next question then is asking us for the general pHs of these substances. So sulfuric acid is, in the first instance, is an acid, obviously generated by the name there, which means its pH is going to be less than 7. Likewise, hydroxide is a common name for, or is a common naming structure for alkalis, which have pHs stronger than 7, higher than 7. But we need to try to evaluate whether or not we're at the strong or weak ends of each of these ranges, and to some extent this requires a bit of memory. We have to remember that sulfuric is a strong acid, so it's definitely towards the 0 to 3 range of pH. It's asking you to state a pH value, so we'd probably just state 1 pH, so we'd probably just say pH of 1, but typically anything between 0 and 3 is okay. Likewise for potassium hydroxide, we have to appreciate that this is one of the stronger alkalis we can get, so we're going to go for pH 14. But again, usually strong range 12 to 14 would be good. And for the salt solution that would be formed, this occurs when we've undergone neutralization. This is the product formed in a neutralization reaction, and so we're looking here for the neutral pH of pH 7. Moving on then, so we're into, again, a typical question here, a question which could turn up on any kind of tier of exam here, this preparation of the salt, how to generate a sample of dry crystals of your salt. And so this one's asking us for describing how the student would safely make dry crystals of a soluble salt, such as copper sulfate, from these two reagents. Now they have given us the two reagents, which is good, and so what we need to do is we take the sulfuric acid, so we're going to add copper oxide, so CuO, to H2SO4, that's our acid. We're going to stir it as well to agitate the reaction and make sure it reacts as well as it can do. So we're going to add the copper oxide to sulfuric acid, and we're going to keep adding the copper oxide until it stops dissolving. So until copper oxide stops dissolving. So we're going to add it essentially until it's in excess. When we know it's in excess, we know that we've therefore reacted all of the sulfuric acid, because as the copper oxide reacts, it appears to dissolve, and so once it stops dissolving, we can then have a good assumption, a good guess that all the sulfuric acid has gone. So once that copper oxide stops dissolving, we'll then be left with a solid. We then have to filter off that copper oxide. So we then have to filter off the copper oxide, which was, as I say, left in excess. So we want to get rid of that excess solid. So once we've filtered off the copper oxide, this will allow us to obtain the copper sulfate solution. So that's the AQ part. So once we've then got that copper sulfate solution, we then need to heat that solution, that filtrate. So we're going to heat the copper sulfate solution, but we're going to do it safely, which means we're going to do it on a water bath. So we're going to do that on a water bath. That allows us to eliminate and evaporate some of the water until some of the water has gone. And in doing so, what that does is concentrates the copper sulfate solution down, potentially makes it a saturated solution, depending on how much water you evaporate. But once we've then evaporated some of that water from the copper sulfate solution, the solution is then allowed to cool, and that process of cooling allows crystallization to happen, and therefore generating crystals. So the solution is then allowed to cool, and crystallization forms crystals. Once we've got those crystals, we can then do a further filtration step. And once we've then filtered those crystals, we would then allow them to dry. That drying process can be by simply leaving them on the filter paper, or by dabbing the top of the filter paper with another piece of filter paper, or by taking the crystals from the filter paper, placing them on a petri dish or watch glass, or even inside just a bigger beaker, and then basically placing them either in an oven or a windowsill in the sunlight, something like that, and just allowing them to dry for a couple of days until all that water is evaporated, and then you've got nice dry crystals. The key to this one being within this method, as they quite often are, is how to safely do that and how to make them dry, which is quite useful as well, being able to make sure you finish off that question. Now in this one, this was a 4-mark situation. Can be 4 marks, quite often can be 6 marks. If it was a 6 mark, we may have given slightly more details of the equipment that we'd have been using, maybe given some volumes for the sulfuric acid and things like that. So there's a few things we could have potentially expanded on here. Could have maybe even drawn a diagram, that would have been useful as well. But for 4 marks, we've probably got enough information in there to generate the question sufficiently. Now, the next question in here, though, does ask us to name one piece of equipment that we would use to safely heat it. So, as we said, we were going to safely heat the salt solution. And so what we would want to do here is we'd want to heat it with a Bunsen burner, I guess. And we could use a hot plate or something like that. But in order to do it safely, I think it's always useful to say Bunsen burner, but it'd be Bunsen burner via indirect heating. Now by that, what we would usually use is some sort of water bath, whereby we would sit the beaker, the evaporating basin, so just a quick diagram here, we'd put our solution that we're trying to evaporate into a dish, into an evaporating basin. We'd sit that on a beaker. That beaker would have water in it, and it's then that water that we would then heat with a Bunsen burner. We probably wouldn't want to heat the Bunsen burner or use the Bunsen burner to heat that dish directly. That's not really regarded as the safest way of doing it. I mean, it will work, obviously, but this indirect heating of using the steam from the boiling water in a beaker to then heat the dish rather than direct heating means that this only really ever gets to a maximum of 100 degrees, because that's the temperature of the steam underneath it. Whereas if you're directly heating this dish here, this dish could get to a couple of 100 degrees at least by the heat of a Bunsen burner. Obviously the water itself would still boil at 100, but this dish, this evaporating basin, could get very, very hot, which isn't particularly safe on your fingers if you accidentally touch it. I mean, a water bath's going to sting a bit if you touch it with your fingers, but if you're heating an evaporating basin, that's going to get very, very hot. And also the rate at which this water will evaporate from this dish means that sometimes you might get it to start spitting and you get water firing out of that dish. Not really safe. It would work, as I say, it's not an incorrect way of doing it, but when a question does specify safety, it's quite often a good idea to do it via some sort of indirect method. Bunsen burner's good, but do it via a water bath method rather than direct heating. So, moving on then, let's go into question 6. We're into a rate of reaction question this time, and it's asking us for simple stating of two factors that can increase the rate of a chemical reaction. One is temperature. Generally, if we were to heat a reaction, that would increase the rate of that. And another would be to increase the concentration. If it was a gas reaction, we may want to increase the pressure. To all intents and purposes are the same thing, depending on the state you're again. It's the state you're in. Concentrations for solutions, obviously pressure for gases, that would be to increase them. So it is asking us to increase the rate of reaction, so we'll make sure we increase the temperature and we increase the concentration. Obviously we could have, if we were also doing solids, we could have also discussed surface area, and we could have also added a catalyst if there was one for the reaction that we were looking at. But it's only asking us for two, so a good starting point for two is concentration and temperature. Now, collision theory is the way in which we explain how particles interact in rates of reaction type questions, and for a reaction to happen, these particles must collide with each other, and in addition to that collision, what must also happen, or what must also be present, the first of those is largely they must have a minimum amount of energy. So that's largely related to what we call the activation energy. So particles must have energy greater than the activation energy. If they don't have that sufficient energy and they're a little bit lower in energy, those particles will simply collide into each other and bounce off each other. But if they collide with sufficient force, it then allows them to react successfully if they've got energy greater than that activation energy. Remember, activation energy is a minimum amount of energy required for a reaction to be successful. And if we're talking about some other types of reactions, the particles must be in the correct orientation. So if the shape of a molecule is specific to a specific type of reaction, then the two molecules must collide with the right area of each molecule's touching, so that they can collide properly and react properly. Biology, when they're talking about enzymes and things, you may see kind of lock and key type situations, and that's what it's meaning by orientation. So we need to make sure we have both of those. For chemistry, largely we're looking for that activation energy though, but as a second requirement, they also have to be in the correct orientation. So moving into the next one then, again using collision theory, it's asking us to explain why increasing the surface area of a solid reactant increases the rate of reaction. So if we increase the surface area, it allows for more exposed particles. So if we've got more particles on the surface, then it allows for more of those particles to be hit by other particles that want to react for it. So if we've got more exposed particles, so it allows for more exposed particles to have more frequent collisions. And importantly, what we'll also state here is more frequent collisions with other reactants. So if you've got A and B, if you've got a larger surface area of A, it allows it to collide with more particles of B. And so remember, we're also here putting the idea of time in here. We're putting more frequent collisions. Try not to simply write more collisions. If you're writing more collisions, make sure you say more collisions per second. But more frequent collisions gets that idea of time in there, which then allows us to make sure we've answered the increasing rate of reaction. So there's two separate points within that one question, and therefore increasing the rate of reaction, as it's stated. So in here, next question, we're looking at marble chips. So quite often this is a standard practical that most people will do during GCSE. This is taking calcium carbonate and reacting with HCl, it's hydrochloric acid, and there's a number of ways we can measure this rate of reaction. Now, one reaction method is to observe the production of the carbon dioxide gas, and so we would measure volume of gas being produced versus time. Okay, volume of gas produced over time. So we would, for example, set up an upturned measuring cylinder, time how long it takes to fill that measuring cylinder, or you may have had a gas syringe or a burette and actually measured the time, the volume produced every 15 seconds or something like that, and produced a graph that way. So either monitoring the time to a fixed point or monitoring gas over time, but we're essentially measuring the volume of gas produced. The other way is to appreciate that as that gas leaves the reaction vessel, so we would have the reactants giving off a gas as they react. That means if that gas is being measured and collected somewhere else and is bubbling out of the reaction vessel, then what happens is the mass of the calcium carbonate, or importantly the mass of the entire reaction vessel, will decrease. So if a gas is allowed to escape from a reaction vessel, the mass will go down. So we could have also measured the loss of mass over time as well, and we would get similar reactions, similar results for both of those experiments. So you could have then subsequently plotted graphs and things like that. So just while we're here, if we were plotting volume of gas, what we might expect to see is that the volume of gas was to increase over time, whereas if we were plotting mass, we would expect that mass to decrease over time. Then we may get something like that, which we could then compare the rates of reactions by changing variables in these experiments, such as the concentration of the acid, or like the previous question, the surface area, something like that. So moving on then into question 7 this time. Here we've got another dot-to-dot question asking us to join these two energy changes, exothermic being the one which gets hot to the observer because that has released energy to the surroundings. It's released energy into your hand, it's released energy into the thermometer, and so the thermometer gets hot, it feels hot to your hand. Whereas an endothermic reaction takes energy in from the surroundings. So if you've got an endothermic reaction going on in your hand, on a test tube, a moderate endothermic reaction in a test tube, that test tube would start to feel cold. The type of reaction that goes on when you click an ice pack. That's a chemical reaction, which is an endothermic one, and is essentially trying to suck the energy out of your hands into its reaction, and so your hand starts to feel cold because that endothermic reaction is taking in the energy from its surroundings. The surroundings being your hand in that case, or the thermometer, and so the thermometer goes down in temperature. So during this reaction, the temperature of the surroundings increases, and so because energy is given out to the surroundings, what that does as a result is the temperature increases in this situation, and so the link there, as we've just gone through in the other direction for endothermic, is if the temperature of the surroundings increases, then that reaction has been exothermic. Now, in exothermic and endothermic types of reactions, what's occurring there is a balance between the breaking of chemical bonds and the making of chemical bonds. Those bonds are broken in the reactants, and they are then made in the products. And the process of breaking bonds requires energy to be put in, and so energy is always taken in when chemical bonds are broken, and energy is always given out when those chemical bonds are made. The easier one to remember, I think, sometimes is that the energy is used to break those bonds, and then via the opposite idea is then given out when those bonds are made on the other way, on the other side. That taken in process relating to those previous definitions is the endothermic process, and the exothermic is the giving out, making of those bonds, and it's that balance between the two. Now, in an experiment such as burning of a fuel, so in this one methanol is burned, so it burns with a flame, it gets hot, so this is a combustion reaction. This is a good exothermic reaction, but in this one they're asking us to balance the equation, so a slightly more complicated example than the previous one we had, but we'll approach it in the same way this time. We've got one carbon on the left hand side, we've got 4 hydrogens on the left hand side. Now we've got 3 oxygens, we've got 1 oxygen in the methanol, and we've got 2 oxygens in the oxygen molecule. Now on the right hand side we've got currently 1 carbon plus a couple of oxygens there, and another oxygen in the water, plus the 2 hydrogens which were in the water molecule. And what we'll see there is that the only element which is currently properly balanced is the carbons, which are 1 each, and also the oxygens, which are currently a total of 3 on both sides. However, we can see that the hydrogens are not balanced in this example. And so what we have to do is try to balance up those hydrogens by doubling the right hand side of the equations where the hydrogens are. So that will give us 2 molecules of water. That will then allow us to change this 2 to a 4. It will also allow us to change this oxygen to 2 as well. Now that, in this situation, has now increased the oxygens on the right hand side. The carbons are still good, 1 each, but now we've increased the oxygens on the right. So we need to increase the oxygens on the left hand side, which means we need to now add in an extra oxygen. So we need to double this oxygen up to 2 again to make it rebalance by introducing a 2 to the methanol. Now what that also does is subsequently changes the carbon, which was okay to start with, and it also changes the hydrogen, which we just fixed. So the hydrogen is now on this side an 8, and here we have now got 2 carbons here. So now it seems to be even more broken than it was to start with, but we keep going. Sometimes equations get more complicated before they essentially get themselves fixed. So the oxygens are now balanced. We've got 4 on each side, but in order to balance those oxygens, we've now subsequently broken the carbons and the hydrogens. So we haven't yet touched the carbons, so we will try to fix the number of carbons. So we've got 2 carbons on the left, we've only got 1 carbon on the right. So this time we're going to double up the number of carbons by doubling up the number of carbon dioxides, which will fix the carbons again, but again, it will break the oxygens. So we now end up with 4 oxygens there, which total 6, but we fix the carbons again. So we've now got 6 oxygens on the right hand side. We've only got 4 oxygens on the left hand side. So carbon is good, oxygen is not good, and hydrogen is not good. Now, so we've got oxygens which are broken and also hydrogens. So we've got 8 hydrogens here and 4 hydrogens there. So what we're going to do this time is double up the hydrogen again by making this into 8 hydrogens. So this will now be 4 waters. This will then give us 4 oxygens. So now we've fixed both the carbon and the hydrogens eventually. We got there in the end. But now the oxygens are broken. However, we're now in a situation where the only number we need to change is this final oxygen here. And now we know that whatever number we put in here is now the final answer. So we've got 8 oxygens on the right. We've got 4 oxygens on the left, which means I'm 4 oxygens short. Now I don't want to change these 2 oxygens because that means changing the 2 in front of methanol, which changes all the carbons and the hydrogens again, and then we go around in a circle. So if we literally just alter this number in this oxygen here, so I need to make this oxygen a 6, which means if I multiply that by a 3, everything is sorted, and that reaction is now good to go. So that's a quite complicated example. It takes a while to go backwards and forwards. There's often no correct place to start. You simply have to keep bouncing backwards and forwards, left and right, until eventually that reaction is completely finished and balanced. But we're now happy. We've got 2 carbons on the left, 2 carbons on the right, 8 hydrogens in total on the left-hand side, together with 8 hydrogens in total on the right-hand side, and subsequently the same for oxygen as well. So, moving into the next question then, to the final part of question 7. A hand warmer uses an exothermic reaction, which is good, but why must that hand warmer be sealed? And so it's suggesting a reason, so it's not asking us to state the very one reason what is going on. So it could be just we use a bit of general knowledge, I guess common sense to some extent. But if we're doing a reaction, essentially an exothermic reaction in our hands, we don't really want chemicals getting on our hands. And so in the use of that, this is just a bit of a health and safety type explanation. So it must be sealed or contained. It stops hazardous chemicals escaping and therefore potentially damaging your hands. Okay, so it stops hazardous chemicals escaping onto skin, or simply stops hazardous chemicals escaping the actual hand warmer, so it essentially doesn't get damaged. So that's a perfectly valid reason. Also, sometimes exothermic reactions in terms of hand warmers actually get very hot, and so the container is used to insulate it and essentially try to make it last a little bit longer, kind of like a thermos flask for your hands. So it kind of helps to contain that heat in there. And also sometimes some of the reactants that are in hand warmers or in many of these kind of temperature changing things, ice packs and things like that, sometimes we simply want to eliminate oxygen. Oxygen will quite often react with quite a lot of compounds and quite a lot of chemicals, and so oxygen getting in there sometimes gets in the way of everything. And so if we want to try and keep it isolated, we would keep it in a sealed container. But I think for this one, the use of a hand warmer, as I say, as it says, as a hand warmer, means it's going to be coming into contact with your skin. And so we don't want those chemicals, which could be hazardous, getting in contact with our skin. So keeping them sealed and contained keeps them away and out of trouble. So question 8 is electrolysis. And again, a dot-to-dot question asking us to line up some of these terms. And it's saying in the first one what an electrolyte is. Now, an electrolyte is often the molten or solution substance in an electrolysis reaction, and this is a substance that is broken down by the electricity. That's the part that's allowing the conduction of electricity to go through it. And the anode, again, this is more of a memory test here. The anode is the positive one, and the cathode is the negative one. So as we go to lead bromide, Again, a common example, a common demonstration, practical here for these types of reaction, whereby you put electrodes into lead bromide, melt it up, and sometimes if you connect it to a bulb, you see the bulb start to light when the lead bromide melts. And this question is asking us too, why must it be melted before it's electrolyzed? And so what we've got is we have to appreciate what is happening when something is being electrolyzed. So in order to carry the charge of electricity throughout its substance, so in order to allow it to conduct, to carry the charge through the lead bromide, we have to have the ability to have A, ions, which lead bromide is ionic, so we've got that aspect. That was like a previous question about the conduction. We were talking about movement of ions, movement of electricity, movement of electrons, allowing substances to conduct. So to carry the charge through the lead bromide, its ions must be mobile. So you must have free moving ions, must be mobile, must be allowed to move. And those ions must do so in order for that charge to be carried. Allowing us to explain why it must be melted, we have to probably explain also why therefore it doesn't do that in a solid. And so in a solid, the ions are in fixed positions. And so if they're in fixed positions, they're not able to move. And therefore, if they're not able to move, they can't carry any charge through the substance, i.e. from left to right in the beaker or something like that, because if those particles can't move, they can't carry the charge with it. So once we get the reaction working, lead bromide, we've got lead ions, Pb2+, in there, and we've also got bromide ions, Br-. And so at the positive electrode, the Br- ions will go towards it, they'll undergo electrolysis, and they will, as a result, produce bromine gas, Br2 molecules, and at the cathode, the Pb2+ ions, or lead, will come out as Pb atoms via their own redox reactions. So some questions may ask you to give those redox equations. We do go through some of those in some of the other papers, so have a look at those. But in this one, it's just asking us to say, this paper has all been designed to be a bit more factual, a bit more rapid fire. So at the anode, we generate bromine, and at the cathode, we generate lead. The idea being, at the negative one, it's the metal that comes out, and at the positive ion, it's generally the non-metal that comes out at that electrode. But the key one to remember is at the negative electrode, you get the metal, and then generally whatever else in the molten substance comes out at the positive electrode. Quite often used as electrolysis to generate the metal. Okay, so that's quite often the more important half that we're looking at in these questions. As it says in the next one, aluminium, so the metal aluminium is quite often is obtained by electrolysis as well. But electricity and electrolysis is an expensive process. And so that increases the cost. And not only is electricity quite expensive, but also the amount of electricity that is needed further emphasizes that cost as well. So there's a large amount of electricity needed, which is kind of a double header there, that you need a lot of it, and electricity is quite expensive anyway. And so if you need a lot of it, it's going to cost you a lot. But for aluminium oxide, one of the advantages to this reaction is that we can mix it with cryolite. Cryolite is an aluminium containing substance, but the function of cryolite in this situation is that adding cryolite to aluminium oxide makes the cryolite act as an impurity. And when we add an impurity to a substance, what that does is it lowers the melting point of the substance we've added to it. So if we reduce the melting point of aluminium oxide, it means we need less energy to melt it. So less energy is needed. And so if we need less energy to melt it, it lowers the cost. That lowering of cost then gets added into the fact that the electricity is expensive in the previous question. So if we've allowed us to save a little bit of energy by lowering the melting point, it makes that reaction just a little bit more financially viable. The electricity still costs a lot, but we've needed a little bit less energy to melt the aluminium oxide. Remembering, we need it molten so that the ions can move, as it was in that question just earlier. The ions must be mobile, so it must be molten. We can't do electrolysis on the solid. So into the final question now. This one's about acids and alkalis. Again, fill in some gaps. Acids react with bases in neutralizations. An acid produces what type of ion? So these are the H plus ions, an acid being an H plus donor, a proton donor, and an alkali producing hydroxide ions, the OH minus ion. So this is hydrogen. It's a hydrogen ion. It's not hydrogen gas. And this one be the hydroxide ion. And so when we then go into a list of 2 different acids and 2 different alkalis, so sulfuric acid and ethanoic acid, together with sodium hydroxide and ammonia solution, we've got to, in this question, identify the strong acid and the weak alkali. Now, in the previous question earlier on, we've already seen that sulfuric acid is a strong acid. We had a pH of between 0 and 3, so sulfuric acid is a strong acid. Ethanoic acid is what's regarded as a weak acid. Like we say, more memory test here, just having to kind of remember which some of these common ones. Ethanoic acid, commonly known as vinegar as well, obviously. So we've got 2 alkalis now then, so sodium hydroxide and ammonia solution. Sodium hydroxide is regarded as a strong one, a strong alkali. Ammonia is a weaker alkali than sodium hydroxide. So again, sometimes, not often, anything we can particularly explain about that. This is just quite often a case of trying to remember these ones. These ones commonly turn up. Ammonia turns up quite a lot in GCSE specs because we have to draw the dot cross diagram of it. But appreciating that it is a weak alkali is also quite useful. And so we've got the pH scale depending on the acidity or alkalinity of a substance. Remember, acidity being demonstrated by things lower than 7. So strong acid down to pH 1, strong alkali being to pH 14. And so if we've got a solution of pH 5 and we dilute it with water, what we're doing is making that solution less concentrated. Now, as a solution becomes less concentrated, the amount of acid in there becomes diluted as well. And so if a solution is becoming a more and more dilute acid, it's essentially increasing its pH. So the pH of something which will go from 5 will go towards 7 by the addition of water. So if we add water, it will dilute the acid, essentially making it less strong, less acidic, and more of an increased pH. won't send it above 7, it won't magically turn it into an alkali, but it will make the pH rise. Likewise, if we were to concentrate that solution down, that would go down the other way. Remembering for those on questions where numerical values are often given, if we change the concentration by a factor of 10, that usually changes the pH value by 1. So if we were to change, we would have to dilute something 10 times to change the pH to 6. And likewise, we would increase the pH by 1 if we made something 10 times more concentrated. Those questions quite often turn up as well. There are some, as I say, on some of the other papers. So 9.4, student uses a titration. So definitely something a little bit more higher tier here, but a type of experiment that we can use to generate concentrations of acids and alkalis. But this question is asking us for pieces of apparatus which are volumes, and is something which allows us to measure volumes, so can turn up on any type of paper really. But two pieces of kit which are useful are burettes. So they are, you may have seen these in the lab, these are long tubes with a tap at one end, and it allows you to measure variable volumes of substances, typically up to about 50 centimeters cubed. And then the other one is a pipette. These being, again, long, thin glass tubes, sometimes have a little bulb in the middle, and long kind of pipe. They sometimes get attached to pipette fillers, whether like the little squeezy ones look like a little balloon, or sometimes more mechanical fillers. So pipettes give a fixed volume of solution, burettes give a variable volume of solution, but slightly more accurate than a measuring cylinder. Measuring cylinders can be useful, but sometimes they're not very accurate in terms of their volume production. And in this question, it's asking us for when an acid and alkali reacts, temperature of the mixture increases. Suggest why the temperature increases. So this is a recall question from something previous, and this is because the reaction in this example has been exothermic. So acid and alkali reactions are typical exothermic reactions. If you add a strong acid to a strong alkali, they will quite often feel warm to the touch, because they're generating an exothermic reaction and therefore releasing energy. So here we have a solution of hydrochloric acid. Now we're told it's got a solution of 0.1 moles per decimeter cubed, so 0.1 moles per litre, if you will, if you prefer litres over decimeter cubed. And here it's been diluted, so like the previous question, we're diluting this from 0.1 to 0.01. So it's going from 0.10 to 0.01. This is a change of 10. So we're changing this by a factor of 10. Whenever we change a concentration, as we said previously, as we change any concentration by a factor of 10, the pH changes by 1. Changes by 1 unit. And in order to answer this question, what we have to do is essentially get the direction correct. So as the pH changes, we are told that we have diluted the acid, and so in the previous question we said that the pH went from 5 towards 7, therefore the pH was going up as an acid became more and more dilute. So in this example, because we're diluting this acid, we know that the pH is going to go up, and because we know it's changed by a factor of 10, we can bring those two things together and say that the pH increases by 1. So we don't know what the starting pH was, but for example, it would go 2 to 3, or 4 to 5, something like that. It would change by 1 unit, and we would be happy with that situation. Okay, so, and there we go. We have finished off this paper, as I say, paper 1 style, but some more factual, more, as I said, joining the dots, more recall type questions, allowing us to get through that paper a little bit quicker, used for, as I say, some quick fire revision. So thank you very much. The paper, as we say, is usable for people studying for foundation or for people studying higher tier if they, as I said, just want some revision of the more factual piece of information required. We will generate a few more of these. There will be 3 of the higher tier versions, direct higher tier papers, and I will generate another 2 of these so that we have 3 of each for paper 1. There will also be 3 of each for paper 2 as well, so find those on the channel when they're available. And I'm also in the process of generating the Trilogy ones as well. They may be up by the time you are listening to this, but thank you very much, and as always, good luck.